This conference will now be recorded.
Hello everyone. Under miscellaneous reaction topic, some reactions, that is 5 reactions we have already discussed, and today we are starting number 6, which is reformance reaction. After this there will be one more reaction under this miscellaneous reaction topic, which is electrophilic substitution. And then we will see the application of aldehyde and ketone molecules, that is uses of aldehyde and ketone molecules, and then we will start carboxylic acids, okay, with structure, nomenclature, occurrence, and derivatives. All these things we will see. So under miscellaneous reaction, Reformatsky reaction number 6. In this reaction here, again we have taken aldehyde or ketone. Obviously it will be present because we are discussing reactions given by aldehyde and ketone. So this will be one of the starting material. Another starting material in this case, as you can see, bromine substituted, and then there is CH2COOR2. So as we have taken R1, so this group is taken as R2. In presence of zinc, we are getting what type of molecule? We are getting beta hydroxy ester. Now this is ester group COOR2. With respect to this group, this position is alpha. This position alpha, this position beta. So at beta position there is hydroxy group, so that is why the name of the compound is beta hydroxy ester. Now how this product we are getting from these two reaction partner, that we will see. So one reaction partner is aldehyde or ketone, depending on whether there is any R group H or not, and the second reaction partner is alpha halo ester. Now again, why it is alpha halo? Because with respect to ester group, this position is alpha, and at alpha position we have halogen. So you can also call it alpha bromo ester because it is bromine halogen. Fine. So what happens if we look into the mechanism? R1, then CHBr CO2 ET. So suppose this is the alpha halo ester. R1 or R2, that is not important. Important thing is it is alpha halo ester. That means with respect to ester group, the position of halogen, it must be alpha. So here, if we take any other halogen, that is ClBr, any of these we can take, but mostly in this reaction bromine as halogen is taken. In presence of Zn, first there will be formation of, see here, carbon bromine bond is broken, and now there is CZnBr. Carbon, then Zn, then Br. You can find some similarity with Grignard reagent preparation method. Remember what we do in Grignard reagent preparation? We take any alkyl halide. Suppose you have taken RBr. In presence of metal Mg, what happens? RBr, that means carbon bromine bond is broken, and in between there is insertion of this metal. So same thing is also happening here. Carbon bromine, this bond broken, and in between these two, the metal, in this case Zn, that is inserted. Now here it is mentioned Reformatsky enolate, and in bracket written carbon Zn enolate. Now what is enolate? Enolate is enol CC double bond, and then there is OH. But if instead of OH there is negative charge, now it is called enolate. Fine. Now here, if we replace this, that is if we consider this hydrogen, which is alpha with respect to carbonyl group of CO2 ET. Fine. So here enolization is possible. Now when enolization is possible, that means as ZnBr is also there, so we are calling it carbon Zn enolate. Fine. Now next there is equilibrium sign. So if you take two of this carbon Zn enolate, and if you write one molecule in this orientation, another molecule in this orientation, both are actually same molecule. Look, R1, then CZnBr, then COOET. So you have to write these two molecules in this way, and there is interaction between Zn and O, which is shown by dotted line. And in this case, if you follow the arrows that are given, this carbon Zn bond is broken, this oxygen Zn bond will be formed, one of the double bond that will be broken, then again this Zn carbon bond is broken, and oxygen Zn bond will be formed, and this double bond is broken, so there will be double bond between carbon and carbon, that is CC double bond. So after this type of arrow moving, if you follow the arrow how it is moving, the structure that you will get now, as we have taken two molecules, there are total two molecules are involved, so you will get now two molecules of OZN enolate. So try to understand the difference. Before this step, there is carbon Zn bond between carbon and Zn, but now there is bond between oxygen and Zn. Zn is not directly attached to carbon, it is now through oxygen attached. So we know when it is O minus and CC double bond, this is actually enolate, both sides there may be any bond, and in this negative charge, if you remove this negative charge and if you write OZnBr, so it is as if oxygen Zn enolate, it is actually enolate, but as there is negative charge, instead of writing negative charge we have written ZnBr, so that is why we are calling it OZn enolate. Next, there is involvement of the actual that is other starting material, which may be aldehyde or ketone, and this enolate, we know when there is enolate, basically when this negative charge is coming back and there is C double bond O bond formation, there will be negative charge at this position. So this negative charge, if this OZN bond broken, there is C double bond O and negative charge will be at this position. So attack will be occurring through this carbon, and as a result this carbon oxygen double bond will be broken. So the purpose of using zinc in this reaction, it allows the generation of an enolate without using any Bronsted base. So normally if you have any molecule where active alpha hydrogen, that is alpha with respect to carbonyl group, if this type of hydrogens are present in presence of some Bronsted base means which can accept H plus, suppose NaOH or KOH. So when you use this type of base, it can capture any acidic hydrogen, there is carbanion generation, and this carbanion it can form some enol. So normally we have seen enol formation in presence of basic medium, but here we have not used any basic medium, right? But still you are getting some enolate. So without using some drastic condition, that is basic condition also, we can produce this type of enolate. So that is the purpose of using Zn, that it allows the generation of an enolate even without using Bronsted base. And ultimately it condenses with the ketone or aldehyde itself. So this RCOR, it may be ketone or aldehyde. So next step is, as I have said, you can directly attack through this carbon, or first you can write this type of interaction. Okay, and as if, see, if you follow the arrows, this oxygen Zn bond broken, there is C double bond O formation, attack is occurring through this carbon, and OZnBr is again formed. The same structure you can also write in chair form, but what happens after all? There is OZnBr, fine, and as we are using acidic condition, C double bond O, that will be formed, because here we will get double bond. This CC double bond, now it is CC single bond, and finally what will happen? ZnBr2. So Zn will be removed in the form of ZnBr2. Okay, so here it is written X minus, which is basically coming from H, that is if you use HX as acid, it may be HBr also. So if it is HBr, as if X minus is Br minus, it is attacking the Zn, OZn bond is broken, and OH. So this is the final beta hydroxy, because with respect to ester group, this is alpha position, this is beta position. So that is why the name is beta hydroxy ester, which is the final product, and zinc is removed in the form of ZnBr2. So initially when we have used zinc, it is metallic zinc, it is zero oxidation state, but now it is class 2 oxidation state, because now it is zinc bromide. Okay, so this is the fate of the reagent, but finally what we are getting? We are getting beta hydroxy ester. And further you can also do some condensation. If you are heating it properly, then there will be CC double bond formation, that is alpha beta unsaturated ester. So this is Reformatsky reaction, which is Why it is so special from other reaction? Because now here we are not using any basic medium, but still we are generating enolate by the use of zinc. Number 7 reaction is electrophilic aromatic substitution. So as we are saying, aromatic substitution, that means it is only for aromatic compounds. Electrophilic aromatic, that means here the aromatic ring that will behave as nucleophile, and from outside the reagent that you will use, that is actually the electrophile. So as the reagent is electrophile, that is electron deficient, so that is why the name is such, electrophilic aromatic substitution. And as we know that aromatic ring, there is pi electron density, so it will be attracted towards electrophile, that is electron deficient species. So that is why it is acting as nucleophile. Aromatic aldehyde or ketones undergo this reaction at the ring in which the carbonyl group of this aldehyde or ketone, that is acting as deactivating group. And when it is deactivating, mostly it is meta detecting, not always, because halogens are also deactivating, but they are not meta detecting. But in this case, they are deactivating and they are also meta detecting. The meaning of deactivating means COR group or aldehyde, because when I'm saying aromatic aldehyde, that means aromatic, that is benzene ring or derivative must be present, benzene ring simple or substituted benzene. And with this, there will be either CHO or there will be some COR group, whether it is aldehyde or ketone. Now this type of groups are electron withdrawing group. That means it will overall decrease the electron density in the benzene ring. So that is the reason we are saying deactivating group. So it will decrease the electron density and it is also meta detecting. That means the electrophile that you are using for this reaction, that will be inserted in the meta position with respect to this group. So the meta position, the hydrogen that is present, that will be replaced by the electrophile, which is E plus. Now depending on what type of electrophile generating reagent you are using, depending on that, there will be different types of electrophile. So as you can see in this case, the example that is given, we are using acetophenone, which is aromatic ketone, and mixture of concentrated HNO3 and H2SO4, which is basically the nitrogen mixture. It will generate the electrophile, which is NO2 plus. This is actually the electrophile, and it will replace any of this meta hydrogen, and that position will be taken by NO2. So the name is meta nitroacetophenone. Now question may arise why it is meta detecting, and for that, to answer that question, you have to understand the resonance structure. So here we have taken very simple molecule which is benzaldehyde. Now the double bonds of benzene ring that can take part in resonance with the carbonyl group of aldehyde or ketone. So this CC double bond, it is taking part in resonance. There is now CC double bond and positive charge will be generated here. And negative charge, though it is not written, it is simply written in terms of that is electrons. See, normally there are 2 lone pair, but now there are total 6 electrons. Basically it is O negative. Fine. Now this positive charge, as it is generated in this position, that is with respect to CHO, now it is at ortho position. Next, this double bond can be shifted. Now the new positive charge is generated at para position. Then further resonance. Now positive charge is here. So see, if you look at this molecule, positive charge is generated at 2 position, 4 position and 6 position. That means 2 and 6, these two are ortho and 4 is para. Now the attacking reagent is E plus. That means it is electron deficient species. So obviously it will not prefer the positions which are already electron deficient. So 2, 4, 6, that is orthopara positions are already electron deficient because of this type of resonance. So E plus will not be interested in ortho or para position. It will be comparatively at meta positions, though I am not saying that at meta position there is negative charge. No, that is not. But with respect to ortho para position, obviously meta positions are less electron deficient. So that is the preferred position for E plus. And this is the reason why it is meta detecting group. Some more examples we will see for electrophilic aromatic substitution. So the first example we have already seen. Now it is for acetophenone, it is shown in the box. but you can also do it for benzaldehyde. Then if you use only concentrated H2SO4, not mixture of HNO3 H2SO4, then what will generate? SO3H. So SO3H, this will be generated from H2SO4, and it is known as meta-benzaldehyde sulfonic acid. So if it is simply benzene ring and SO3H, it is known as sulfonic acid, but there is also CHO group at meta position. And see here also meta position, the electrophile is inserted. If you are using concentrated FeCl3 it is catalytic. It is catalyst. FeCl3 is catalyst, and you are using chlorine. You will get metachlorobenzaldehyde. So here electrophile is basically Cl+. Now the same type of reaction, that is again if you are using chlorine but without any catalyst, now the reaction is completely different. It is not electrophilic aromatic substitution, because here see what is the reaction. It is simply the replacement of this H which is attached to the carbonyl, that is replaced by Cl. So there is no reaction occurring at the aromatic ring itself. It is occurring in the CHO group, right? So that is why, though this reaction is not under this, but still it is here so that you can compare, because you may get question that when benzaldehyde or any other aromatic ketone, it is treated with chlorine in presence of catalyst and without catalyst. What is the difference? Is it same reaction or different? So when it is in presence of catalyst, the reaction is basically electrophilic aromatic substitution. But if you are not using catalyst, the reaction will be something else. So try to understand the difference. Okay. So the last one, that is not electrophilic aromatic substitution, when you are not using any catalyst. Now uses of aldehydes and ketones. Formaldehyde. Formaldehyde means H C double bond O H. So this is the most simple aldehyde that is possible, because we know in aldehyde there must be one hydrogen, but the other side there may be alkyl group or hydrogen. So the simplest possibility is if there is hydrogen. So now there is both side hydrogen. Now formaldehyde, if you take 40% aqueous solution, then there is a specific name for this solution which is formalin. Now this solution is used for preserving purpose of different biological specimen, which is also called sometimes embalming. That is, you are increasing its lifetime for preservation purpose. Then formaldehyde can also be used in tanning, preparing glues, polymeric products, and also see, so huge application, germicide, insecticide, and also fungicide for plants. So if we use this solution, we can save plants from all these germs, insects, fungi, etc. Then formalin used in the production of thermosetting plastic. Thermosetting plastic is basically when you heat it, you can change its shape, and once when it is cool, that is in cold condition, now it is in solid form. Now you cannot change its shape. So only when in heated condition you can change its shape. So this is known as thermoplastic, thermosetting plastic, and formalin used for this. And this plastic also known as bakelite. So how formalin is used? Basically, when we heat phenol with formalin, phenol is benzene ring with OH and formalin, we get this type of polymer. It is actually polymer. Acetaldehyde, the next aldehyde structure that is possible. It is used for silvering of mirror. Remember tolerance reagent? In tolerance reagent, we use Ag+. That is not directly Ag+. Ag+ is actually the oxidizing agent. Now acetaldehyde, it has reducing property. It will reduce this silver plus to metallic silver, that is Ag0, and we know there is metallic silver formation, which is basically the reason for this type of mirror. So acetaldehyde is used for silvering of mirrors. Then paraldehyde is used in medicine as a hypnotic, that is sedative purpose. So this is the structure of paraldehyde. CH3CO, if you take 3 molecules, then only you can get this. Just if you imagine this type of fragment, basically 3 CH3CO CHO fragments are there, right? So acetaldehyde is largely used also for the production of acetic acid, that is CH3COH. Acetaldehyde is CH3CHO. If you oxidize it it will be converted to acetic acid. So for acetic acid production, which is also having some other application. So for this important molecule synthesis, you can use acetaldehyde. Then ethyl acetate, which is ester, some pyridine derivative, etc. All these molecules can be produced from acetaldehyde. Benzaldehyde, that is aromatic aldehyde, PHCHO, used in perfume, cosmetic products, dyes, added to provide unknown flavor to food products. So it has some specific flavor. Bee repellent, starting material for the synthesis of several other organic compounds, for example, cinnamaldehyde. Fine. So from cinnamaldehyde you can also produce cinnamic acid. So in this way, acid chain system, that is benzaldehyde is important because it can produce cinnamaldehyde, then from cinnamaldehyde you can produce cinnamic acid like this. Fine. Benzoyl fluoride, that is PHCOCl. Benzaldehyde is PHCHO. And PHCOCl is benzoyl chloride. Remember when in the last slide what we have seen, when you are treating it with chlorine without any catalyst, this H is replaced by Cl. So now it is converted to PHCOCl, which is nothing but benzoyl chloride. Don't be confused with the spelling. When it is benzyl, BENZYL, it is PHCH2Cl. But when I am saying benzoyl, now there is double bond. So this is the difference in spelling. Aliphatic ketones. The most common ketone is acetone, obviously. That is the first member of ketone, aliphatic ketone. Excellent solvent for a number of plastic and synthetic fibers. Then in the household, acetone is used as nail paint remover, paint thinner. So why it is possible? Because it is soluble in acetone. So that is why we can use it as paint remover or nail paint remover or paint thinner. In the preparation of sulfonal, which is again a hypnotic, this is the structure of sulfonal. In medicine, it is used in before chemical peeling and for acne treatment. So chemical peeling, that is before starting the process, chemical peeling is actually used for better to enhance the quality of skin, and before this there is use of acetone, then chemical peeling is done. Also for acne treatment, then manufacture of thermosoftening plastic has a specific name, perspex. Methyl ethyl ketone. So after acetone, up to this we have seen acetone. Now methyl ethyl ketone, in short it is also known as MEK. Methyl ethyl ketone means methyl group one side, then CO, then ethyl group on the other side. That is methyl ethyl ketone. You can also call it butanone because it is 4 carbon, right? Is used in the production of textile varnishes, plastic, paint remover, paraffin wax, etc. So many different types of applications. Then in a welding agent for plastic due to its dissolving properties. Then another ketone, cyclohexanone, that is ring structure. This is cyclohexanone. Another important ketone which is primarily used in the production of nylon, which is a polymer. Next is aromatic ketones. In general, if we see, good example is, that is the simplest example, better I say, PHCOCH2, because both sides there must be some group. Now minimum what group you can take in? 1 carbon, which is methyl. This is the simplest structure for aromatic ketones. In perfumery, hypnotic, and as a hypnotic under the name hypnone. Benzophenone, PHCO, then again PH. This this compound is used in perfumery again and in the preparation of benzhydrol. So these are the uses of different types of aldehydes and ketones. So now we will start carboxylic acid, the last important compound for this chapter. Carboxylic acid, this is the structure, as you can see here, COOH groups are present. So carbon compounds where you will find carboxyl functional group. So this group we are calling it carboxyl. Now why we are calling it so? Basically they are carboxylic acid, but the group is called carboxyl functional group. Now carboxyl group is combination of two terms. One is carbonyl group, which is P double bond O. Carbonyl group C double bond O, and hydroxyl group. So this is carbonyl, this is hydroxyl, but together it is carboxyl. Carboxyl group has its own characteristic reaction. So though it is a combination of two groups, C double bond O and OH, but don't think that they will give individual reaction of C double bond O and OH. That is alcohol and keto compound. No, it is not that. When you are combining these two groups together, now they will have their own characteristic properties. The chief chemical characteristic of this acid is their acidity, and that is clear from its name. In the name itself, we are using the term acid. So it must have some acidic property, right? They are generally more acidic than any other organic compounds containing OH group. So obviously, compared to alcohol, they are more acidic, but are generally weaker than the familiar mineral acids. So if you think about the inorganic acid, that is HCl, H2SO4, they are not organic acid. We call them mineral acid. HCl, H2SO4, obviously carboxylic acid, they are not so acidic like these acids, but they are more acidic than other organic compounds where OH group is present. Remember? So that is why it is more mainly in organic compounds, because compared to inorganic acids, it is not so acidic. But in organic compounds, these are the most acidic compounds. Here we have some pictures of different types of carboxylic acid. So all these example, you will not find any aromatic ring. It is only for aliphatic compounds. So the names that you are seeing here, these names are basically common names. We will also see how to use the IUPAC names. Some aromatic carboxylic acid, that also you can see. So this is the simplest aromatic acid possible. Then we have methyl substituted acid. At ortho position there is methyl, salicylic acid, then anthralinic acid. NH2 at ortho position, meta-nitrobenzoic acid. Meta is present at meta, there is NO2 group present. Now phthalic acid, it is actually dicarboxylic acid at 1 and 2 positions. So some examples of aromatic as well as aliphatic carboxylic acid you can see. And sometimes in some molecules you will see there are two CO2H group. For example, CO2H group, then CC double bond CO2H group. This is fumaric acid. Then again two CO2H group. In between these two groups there are CH2 chain. In this malic acid we also have a OH group. Pyruvic acid, there is CO2H group, but there is also carbonyl group. At alpha position, OH group present. Citric acid, this is interesting. You will find total 3 carboxylic acid group. And then there is OH also. Gluconic acid, so many OH groups are there. And 1 CO2H group. Fine. Occurrence. Now, occurrence means that natural presence. There are different compounds in which they are naturally present. So they occur widely in nature. Some higher members of aliphatic carboxylic acid. Higher member means where carbon chain, it is from C12 to C18. Total number of carbons from 12, 13, 14 up to 18. They are mainly called, that is when the carbon chain is very long. It is from 12 to 18 like this. They are known as fatty acid. They occur in, why the name is so? Because they occur as natural fat as ester of glycerol. So they do not remain as free carboxylic acid. They remain in the ester form. Ester of which alcohol? It is glycerol. So in glycerol there is OH group, and in the fatty acid there is CO2H group, and reaction between acid and alcohol that will produce ester. That is actually the natural fat, its structure. Fine. So in this, that is in the ester form, ester of glycerol molecule, these acids are present. Not directly as acid, but in the form of ester, they are present naturally in fats. Hydroxyl acid. Hydroxyl acid means OH group is there, CO2H group is also there. Such as lactic acid, then citric acid. Lactic acid found in sour milk products, for example, curd. Then citric acid found in citrus fruit. You can also find a similarity, that is why the common names are so. It is basically found in citrus fruit, so that is why the name is citric acid. Then many keto acid. Keto acid means carbonyl group is also there. CO2H group is there, carbonyl group is also there. These keto acids are important metabolic products that exist in most living cells. Then proteins, very important. We know basic, that is small units are amino acid. When they are connected to each other, we get the structure of protein. Now in amino acid also, there is NH2 group, there is CO2H group. So that is why the name is amino acid, because of the presence of amine and carboxylic acid. But carboxyl group is present. So natural occurrence is very wide. Derivative. Now derivative, when we are saying, that means general structure is RCOOH. But instead of writing OH, if I write Z, this will be called as derivative. So these Z may be different types of groups. When the OH of carboxyl group is replaced by certain other groups, we call these molecules carboxylic acid derivatives. Now the important class of organic compounds. What we know? We know alcohols, general formula ROH, phenol, PHOH or AROH if it is substituted benzene, then ether ROR, amine RNH2, halides RX. So all these are different important classes of organic compounds, right? Now in these compounds, there is presence of different groups: alcohol OH, phenol OH, ether is presence of alkoxy, amine there is presence of NH2, right? So what happens? All these compounds, they consist of alkyl and aryl or aryl groups bonded to hydroxyl in case of alcohol phenol, alkoxyl in case of ether ROR, then amino or halo. So when I'm saying amine compounds, that means it is RNH2. So that is why it is mentioned here that either alkyl group or some aryl groups are attached to amino, or if it is attached to halo, that is RX, or maybe alkyl or aromatic, then it will be the halo compounds. So these are the different important compounds. Now the same functional group. Which functional group? OH, OR, NH2, halo. All these functional groups, when they are in Z form, that is after, instead of writing OH, if you write RCONH2, RCOCl, RCOOR, depending on that, you can get different derivatives. See, if the same functional groups are attached to an acyl group is basically, this part is known as acyl group, RCO. So when different groups in the, that is as Z, it is attached to some acyl group, which is RCO, their properties are substantially changed. That is, compared to RCO2H, when you are changing the OH to some other groups, it is its properties have completely changed. They are designated as carboxyl acid derivatives. So here you can see RCOH, which is actually carboxylic acid. When OH is replaced by X, it is acid halide. X may be ClBr. Then when it is OR prime, that is alkoxyl group, then it is known as ester. When this OR group is OCOR group, now it is called anhydride. When the Z is NH2, it is called amide. So these are the different derivatives and their properties are obviously different, right? Structure of carboxylic acid. The carbon and oxygen in the carbonyl, that means if we consider the structure RCOOH, so this carbon and this oxygen both are sp2 hybridized, obviously they are doubly bonded, which gives a carboxylic acid a trigonal planar shape. So trigonal planar shape around the carbonyl carbon. So around this group, if you consider the structure, it is trigonal planar, which is because of this sp2 hybridization of carbon and oxygen. Here resonance structure is possible. So what type of resonance? RCOOH, right? Now the lone pair over this OH, if it is making a OC bond, this pi bond is broken, there will be negative charge. So the structure will be now O minus CC double bond OH. H and oxygen is positive because total 3 bonds are there. So these two are the resonance structure. A resonance structure exists where one of the lone pairs of the hydroxyl oxygen, that is this OH, oxygen's lone pair, it is now conjugated with the pi bond system of the carbonyl group. So this is the resonance that is possible. When it ionizes, that is RCO2H, as it is acid, it can ionize 2H plus and RCO2 minus, that is negatively charged oxygen, and this RCO2 minus, it is known as carboxylate ion. So see, this is normal form, that is RCOOH. Now after ionization, you are getting carboxylate ion. Now this carboxylate ion, there is negative charge over oxygen and H plus. Now here also resonance is possible, just like we have done the resonance in the non-ionized form. So this is the non-ionized form, right, where resonance is possible. See, this structure I have already drawn here. Now when it is in ion form, carboxylate ion, now the resonance that you are getting, so suppose this is structure 1, this is structure 2. Now look at structure 1 and structure 2. Both are actually alike, same structure, right? And when in resonance we get same structure, the stability is really very high. So both are actually relatively stable. But when it is in non-ionized form, now if you look at the resonance contributor, so these two are actually resonance contributor. These two are also resonance contributor, but they are resonance contributor for carboxylate ion, not the non-ionized form, it is ionized form. But if you consider the resonance contributors of the carboxylic acid itself before ionization, now you are getting these two structures, and these two structures are not same. Now when we choose that which resonance structure is more stable, there are obviously some rules, and one of the rule is you have to choose that structure as more stable which is having less charge. Now the first molecule, that is a normal form, there is no charge present, but in the second form there is negative charge, there is positive charge. So obviously this form is more stable, so that is what is written here, relatively stable, this is relatively unstable. But when you consider the ionized form, that is after removal of H plus, now both the forms are same. So carboxylate ion formed is extremely stable because of resonance. The carboxylic carbon is less electrophilic than carbonyl carbon because of delocalization. Now what is the meaning of this line? The meaning is, it is trying to say, if you simply consider any carbonyl compound, it may be RCOR, ketone, or it may be aldehyde. Now in these two molecules, this type of resonance is not possible because there is no such group with lone pair, both sides. So this type of resonance is not possible. So as a result, now what is happening? The double bond character of the C double bond O group, that is very high. And as a result, the carbon of aldehyde or ketone, this carbonyl carbon is highly electrophilic. But if you consider resonance structure that is possible in case of carboxylic acid, now in first structure you can see there is double bond between carbon and oxygen, but in the second structure after resonance, now it is single bond character. So as a result, what will happen? The electrophilic character, that is electrophilic means it is electron deficient, it will prefer attack from nucleophile. But if its electrophilicity is decreased, the tendency of the nucleophile, you can consider in general any nucleophile, the tendency of attack, that will be very, very less. So when it is C double bond O form, now the nucleophile, it will prefer it more because now the electrophilic character is more. So here after resonance, the electrophilic character is decreased. So if you compare the electrophilicity of these two carbon, that is I am talking about the carbon in aldehyde and ketone and the carbon in carboxylic acid. So obviously in aldehyde and ketone, here nucleophile, it will prefer to attack at these positions because here this type of that is decrease in double bond character of carbonyl carbon, that is not present. So that is why it is written carboxylic carbon is less electrophilic than carbonyl carbon that is present in aldehyde or ketone because of this type of delocalization. And after delocalization, that is if you consider the ionic form. So here it is written as if it is sodium salt. Just consider the ionic form RCOO minus, but suppose it is Na. That is, if you are treating it with NaOH, so H plus will be removed and that place will be taken by the metal Na plus. Now, if you consider these two resonance structure, if you draw the average, this is actually the average structure where negative charge it is written in this way. That is, it is present over both these oxygen. So if you consider the average structure, now the bond distance it is around 1.27 angstrom. But if you consider the non-ionized form, now there is C double bond O, which is obviously the bond length is less because double bonds are always shorter. And here we have single bond, which is 1.34 angstrom. But when you consider the average structure, that is partial double bond is present. Now the value that you see compare, it is in between 1.20 and 1.34 because it is not fully single bond, it is not fully double bond, it is something in between. So that is why the value is also like this. So that is all about the structure of carboxylic acid. Next is nomenclature of carboxylic acid. The IUPAC name of a carboxylic acid is derived from that of the longest carbon chain that should contain the CO2H group. Now in this case, if instead of alkane, if you have some CO2H group, which you can see here, this is pentane molecule, right? But same molecule, any of these three hydrogen, if you replace with CO2H group, now the name is pentanoic acid. How you are getting it? So when it is the parent alkane compound, it is pentane, but now you have to drop this final E and you have to add the word term oic acid. So now look at the name, it is pentanoic acid, and you have to drop the final E from the name of the parent alkane and you have to add the suffix oic acid. So for CO2H, the suffix that we use is oic acid. And you have to start the numbering from the that carbon, which is the carbon of CO2H group. So the chain is numbered beginning with the carbon of the carboxyl group. So you can see here, this is the carbon of CO2H group from which we have started the numbering. Now, if we compare priority of different functional group, suppose OH, NH2, CO2H, if you compare this priority of this group, carboxylic acid is having the highest priority. So it has higher priority than any other functional group. So that is why you don't have to think which group will be used as suffix. It is always CO2H group which will be, that is for which we have to use the suffix because it is having the highest priority among all the groups. So always the suffix will be oic acid. They define the parent chain and give the corresponding suffix to the compound's name. It is always oic acid, irrespective of what other groups are present, whether OH, any halogen or NH2, always it is oic acid. We will see examples. In this molecule, the longest chain, if you consider here, numbering we have already done, starting one from the carbonyl carbon of CO2H and it is ending here. Now in this longest chain, at 3 position we have methyl group, at 4 position we have bromine. Now bromine and methyl, if you consider alphabetically, B is coming before M, so that is why though its position is 4, here position is not important, important is alphabetically which is coming first. So 4 bromo, then 3 methyl, these two are substituent, and that is why we are using the prefix bromo and methyl, 4 position, 3 position. Then as usual, that we have already seen in the first example, pentane is converted to pentanoic acid. In this case, it is hexane. Parent alkane is hexane, but we will drop the E and we will add oic acid. Longest chain is 6 carbon. Next example. Here, longest chain in the red color that you can see, it is containing 7 carbon. 3 position, obviously numbering would be started from this carbon. 3 position, cyano group. 6 position, there is fluorine. Now among chlorine and cyano, C is coming before F. That is why 3-cyano 6-fluoro heptane is converted to heptanoic acid. And if you are thinking that why not nitrile, because nitrile term is used when cyano is having highest priority. That is when CN group is used as suffix. But when it is prefix, we cannot use nitrile. Then you have to use cyano. So that is why it is cyano here, because CO2H highest priority, not CN or F. 3-cyano 6-fluoroheptanoic acid. If in the molecule you also have carbon-carbon double bond, then what will happen? That means in these examples, there is no CC double bond. So all are basically alkane derivative. But if it is alkene derivative, now the ending will change from anoic acid to enoic acid. So in these examples, you see the ending is basically anoic, isn't it? In all these examples, it is anoic, but now it will be enoic. Enoic in the sense it is coming from in. So here the longest chain 1, 2, 3, 4, 5. But at 3 position there is double bond present, and it is also trans. So when there is CC double bond, the question of cis trans or EZ arises. So we have mentioned it as trans. Then 3-pentenoic acid. So it is actually pentenoic acid, but if you do not mention 3, then simply looking at the name pentenoic acid, suppose structure is not given, but I'm saying that it is trans-pentenoic acid, it doesn't make any sense. How we will understand that what is the position of CC double bond? So position of CC double bond must be mentioned. So if I am writing trans-3-pentenoic acid, now you can draw the structure. So always, if you have any confusion that you have structure, you are writing the name. And if you want to know whether it is fine or not, the reverse process also you can do. Suppose you do not know the structure, the name is given, just check yourself whether you can draw the structure or not. So if you do not mention 3 or if you do not mention trans, then structure we cannot draw properly. Next example, here not just CC double bond, we also have some methyl substitute. This is 1, 2, 3, 4. So longest chain is 4 carbon. Methyl substituent present at 2 position. At 2 position there is also double bond present. So 2 methyl, 2 butanoic acid. If there is no methyl, it is simply 2 butanoic acid, just like the previous example. But now there is methyl group. So 2 methyl and also E is mentioned. 2 methyl, 2 butanoic acid. Okay. So these are the rules for that is when it is non-cyclic compound. Here the examples that you are seeing all are non-cyclic. Some examples we'll see where prefix, root word and primary suffix, secondary suffix all are individually shown. Here in the left hand side column, first there is common name, then the structural formula, then the IUPAC name. So common name mostly used for some acid. We will come to that point later. Right now just focus on how we are writing the IUPAC name. This is the simplest acid, formic acid, and it is known as methanoic acid. Now why it is so? Here we do not have any prefix. Root word is meth because it is single carbon, longest chain single carbon. And primary suffix is basically the parent alkane. So alkane is ending with ane, but here as it is not alkane actually, it is the derivative, that is if you replace hydrogen of alkane with CO2H, then you are getting this. So that is why the secondary suffix used, oic acid, this E we will not use, it will be omitted, and an then oic acid. So that is why an then oic acid. Sorry, there will be gap. Then the next member possible acetic acid, but that is not IUPAC name. IUPAC name is ethanoic acid. Why it is so? No prefix, longest chain containing 2 carbons. So right now it is eth. It is alkane derivative, but ultimately E will be removed and we will write ethanoic acid. Isobutyric acid. This is common name, but IUPAC name is 2-methyl propanoic acid. So 2-methyl propanoic acid means COOH. This is 1 carbon. Prop, that means total 3 carbon. 2 position there is methyl. So this is methyl. This is 2 position. This is 3 position. Right? Longest chain 3 carbon. There is also prefix at 2 position. So 2-methyl prop for 3 carbon. It is alkane derivative AN. E is removed. Then oic acid. Phenyl acetic acid. Now we also have a substituent, that is, it is actually ethanoic acid, just like this one, acetic acid, but as if you remove one of the hydrogen of methyl and you place a phenyl, so there is prefix, that is substituent phenyl is present at 2 positions, so that is why the prefix 2 phenyl. Then as usual ethanoic acid, as you have seen in the case of acetic acid. Some more examples. Now we have dicarboxylic acid. Now for dicarboxylic acid, the rule is slightly different, though this same rule you have also seen in case of ketone and aldehyde, that when 2 same groups are present, then there is slight change. And what is the slight change? The slight change that we have here we have dropped all this E, right? But we will not do that. So in this box, all these are basically containing 2CO2H and E will not be dropped. Fine. So look at the name. There is no prefix. Root word is eth because it is containing 2 carbon, 1 and 2. And eth, that is ethane. It is actually ethane. But at 1 and 2 position, there is oic acid, 2 CO2H, so that is it is dioic acid. So don't drop the E. You have to maintain the E when there are 2 CO2H. Then CO2H, CH2CO2H. In between these 2 CO2H, you have 1 CH2 extra. So now the longest chain is 3 carbon. So it is prop, then N, and you have to mention the position of acid. It is at terminal position 1 and 3. Then butane dioic acid. So gradually we are increasing 1 carbon. So it is but N 1 and 4, terminal position. This is pentane dioic acid, then hexane dioic acid. So gradually we increase carbon 1 by 1. The names will be changed in this way: 1 4, 1 5, then 1 6. Fine. So remember, when it is di, 2 CO2H groups are present. Don't remove this E of alkane, that is primary sub. Now what about common names? Sometimes if it is very simple carboxylic acid, then we use common names. And sometimes common names are derived from that is their occurrence. So suppose that is, for example, you have seen the names lactic acid, citric acid. So these common names are basically related to their occurrence. For example, citric acid is found in citrus fruit. So the name is citric acid. So here we have the common names, and also we have in the next column the systematic name, so that you can compare the both. Though there is nothing to compare, basically from the systematic name you can compare with the structure. So single carbon ethanoic acid, then acetic acid, it is ethanoic acid. We have just seen all these IUPAC names, but common names are formic acid, then acetic acid, propanoic acid, though you can find some similarity, but actually these names are not based on any IUPAC groups. Valeric, stearic, benzoic. These two names same. Fine. Now some dicarboxylic acid. General formula, if you follow this, CO2H, then CH2 linkage with N value. Now this N value, it may be 0 to 8. So when it is 0, it is basically oxalic acid or ethane dioic acid. Remember, these names we have seen in the previous slide examples we have seen. So IUPAC name we have already seen, but common names are, now there is no other way except you have to memorize all these names. Though all this, that is very large structure, probably even if you cannot remember, it is fine. But up to this, it is helpful to remember, because if in the problem it is given with the common name, suppose a problem is given mentioning that succinic acid or glutaric acid, so if you do not know, if you don't have prior knowledge about their structure, you will not be able to solve the problem, right? So that is why here common names are given. Gradually we are increasing this value of N0 up to 8. Fine. Naming carboxylic acid when it is present in ring, that means cyclic structure if we have. Now what will happen? When a carboxyl group is added to a ring, now the suffix carboxylic acid is added to the name of the cyclic compound. The ring carbon attached to the carboxyl group is given the location number 1. Now this is a very important point. When it is open structure, what you have seen? You have started the numbering from that carbon, which is basically the carbon of CO2H. But if it is attached to some ring structure, suppose you have any ring structure and then there is CO2H. I am writing in this way to as if I am trying to say it is general. It may be 4 members, 6 members, 7 members, whatever. But you cannot start the numbering from this carbon when it is cyclic. You have to start numbering from this carbon with which it is attached. This is a very that is drastic difference. If substituents are also present, okay, we'll come to that point. First, try to understand. See, the numbering we have started from this carbon, not this one. Fine. If substituents are also present, the numbering starts from the carbon connected to CO2H group and goes in that direction. That minimizes the numbering of the substituent. So here the first structure is actually accepted, not the second one, because in the second one the direction is like this, from CO2H to Cl, 1, 2, 3, 4. You are getting the position of Cl4. But if you move in this direction, another possible direction, now it is getting the number 3. So you have to move to that direction where you are getting minimum numbering for the substituent. So that is why the first structure is accepted. Now look at the name, 3-chloro-cyclopentane, then carboxylic acid. So in case of open structure, what you have seen? Alkane, you have removed the last E, then you have added oic acid. But here it is not oic acid. You have to write the full name, which is cyclopentane, then you have to write carboxylic acid. So it is completely different when it is open structure. Now in this structure you can see CO2H group is not directly attached to ring, but still I have used this example here so that you can understand this. You can understand the difference. It is actually open structure. That is, you have to follow the IUPAC rules that you have done for open structures. That is why one is started from this CO2H carbon and you have to find the longest chain. It is the longest chain in blue color because it is containing CO2H group. At 2 position you have propyl substituent, at 3 position you have phenyl substituent. So that is why the name 3-phenyl, then 2-propyl. Now both are P, but the next is H. Here it is R. H comes before R. So that is why 3-phenyl, then 2-propyl, and then as usual pentanic acid. So this example is not for, that is, naming carboxylic acid on a ring, but I have mentioned it so that you can understand the difference. Now some more examples. So we are at the end of the session. These examples, 2 to 3 examples, we'll discuss in the next class. Thank you for listening. We are ending the session here.